this is Eloisa with Math Leopard. Today I'm going to discuss how to derive the formula for curvature, kappa. First, I would like to consider three circular arcs, one large, one medium, and one small. If we traverse a fixed distance across each arc, we note that in the case of the largest circular arc, the distance amounts to but a fraction of the overall circumference. In the second instance, the distance is nearly half the circle's circumference, curving through nearly 180 degrees. In the final case, however, the distance has traversed the entire circumference, and hence has curved through 360 degrees of arc to meet up with itself once more. We note that the smaller the radius, the more curvature our fixed length encounters. Let's consider the graph of a curve C, seen here in blue, traced out by the vector r of t, defined component-wise by the functions f of t and g of t. As the tip of our vector moves through time, the curve will have instantaneous tangents. We note that this first tangent with respect to the positive x-axis makes an angle theta sub f, whereas moving further along the curve, a second tangent produces an angle theta naught with respect to the direction vector I. As this is a smooth curve, the distance between these two tangents can be inscribed with a circle whose circumference is coincident to the graph. We note this in red. We now project this distance down onto the x-axis and note that it corresponds to the change in arc length, s, with respect to x. The curvature, kappa, is the quotient between the change in angle and the change in arc length. That is how much we are curving with respect to the circumference. Recall in our initial three images, the greatest curvature occurred along the circumference of the smallest circle. That is, the circle on which the change in angle was greatest. Referring to our illustration, we note that the change in angle, measured counterclockwise, is the difference of theta sub f and theta naught, whereas the change in arc length can be annotated as delta s. Expressing the difference in the numerator as delta theta, and then dividing both the numerator and the denominator by delta x, we arrive at the following quotient, which, in the limit, changes from the measurable, or Greek notation, to the immeasurable, or English notation, d theta dx over ds dx. Recall that this two-dimensional curve was traced out by the vector r of t, with first component f of t, and second component g of t. This implies that the tangent vector r prime of t is given by f prime of t and g prime of t component-wise. This tangent vector gives us the slope of the tangent line at any point t, namely the quotient of g prime of t and f prime of t. This in turn is the instantaneous value for the tangent of theta, given f and g are twice continuously differentiable. We can isolate theta in the expression above as arctangent of g prime of t over f prime of t. However, before proceeding, let's recall that the derivative of the inverse tangent function can be derived by setting theta equal to inverse tangent of x. We then express this equivalently as x equal to tangent of theta. At this point, we are able to take the derivative of both sides of this equation with respect to x, yielding 1 is equal to d theta dx times secant squared theta, by way of the chain rule. Isolating d theta dx, which, given that we've identified arctangent of x as theta, is what we're actually trying to find, we arrive at the quotient of 1 and secant squared theta. We recall from our Pythagorean identities that 1 plus tangent squared theta is equivalent to secant squared theta, and substitute the former for the latter. Given that tangent of theta is equivalent to x, we now have the identity for the derivative of arctangent, namely 1 over the sum of 1 and x squared. Let's apply this to the formula above by taking the derivative of theta with respect to x, and equating that to the derivative of inverse tangent of the quotient, g prime of t and f prime of t. Using the chain rule once more, we have that this is 1 over 1 plus the quotient of g prime of t and f prime of t squared, all times the derivative of that same quotient. Rewriting this, we have that d theta dx is given by 1 over the sum of 1 and the square of the quotient of g prime of t over f prime of t, all multiplied by the derivative of g prime of t over f prime of t. We then use the quotient rule to find the derivative of g prime of t over f prime of t, yielding f prime of t times g double prime of t minus g prime of t times f double prime of t all over f prime of t quantity squared. Notice that by distributing this derivative to the quotient that preceded it in the product above, that the square of f prime of t in the denominator eliminates a complex fraction, giving us the sum of the squares of the components of r prime of t in the denominator. Let's place this momentary monstrosity in the numerator of kappa back on top, while simultaneously replacing ds dx with its more familiar Pythagorean form. But let's make sure that this is indeed a valid means by which to express the arc length. Arc length S can be thought of as the sum of the lengths of each of n partitions of a curve between a and x. That is the square root of the sum of the squares of the differences in x values, delta x, and y values, delta y. We then multiply this expression by a very specific 1, namely the quotient delta t over delta t, pushing the denominator delta t underneath the square root, thereby squaring it. The argument inside the root now becomes the square of delta x over delta t plus the square of delta y over delta t. Therefore, the arc length function can be expressed as the limit of this sum, once again going from Greek sigma to English elongated s, with the integral from a to x of the square root of the sum of squares of dx dt and dy dt. That is, the sum of the squares of each component of our vector r prime of t. Hence, by the fundamental theorem of calculus, taking the derivative of an antiderivative with a variable upper limit of integration gives us the integrand. But this integrand is the magnitude or quote norm of our vector r prime of t. Recall, the magnitude of the cross product between the first and second derivatives of r of t is given by the determinant of the 3×3 Wronskian matrix, whose third, or k, component is 0. This simplifies to the determinant of the lower left 2×2 matrix. That is the product of the main diagonal, f prime of t times g double prime of t, from which we subtract the product of the alternate diagonal, g prime of t times f double prime of t. Therefore, we have that the curvature kappa from above can be simplified by first combining the two denominators into one, that is, the sum of the squares of the derivatives of f and g, quantity to the 3/2 power. We then rewrite the 3/2 power by expressing the denominator as the cube of the square root of the sum of the squares of the derivatives. Hence, we arrive at the final form for the curvature of a curve C, traced out by a vector r of t in the plane. It is the quotient of the magnitude of the cross product of r prime of t and r double prime of t over the magnitude of r prime of t cubed. Thanks for playing, and I'll see you next time.